Welcome to the June talk in our seminar series, which aims to provide accessible introductions to some of the most significant mathematical theorems of the 21st century. Today's talk will last about 50 minutes, followed by time for questions and discussions. Please feel free to type your questions and comments at any time at the meeting chat. At the end of the talk, when will be time for questions, I will unmute everyone and you will be able to ask your questions in voice. So it is my great pleasure to introduce our today's speakers. It's a joint talk of Professor Andrew Lobb and Professor Josh Greene, who are leading mathematicians whose work has made important contributions to several areas of geometry topology. In this talk, they will discuss recent progress on classical encryption problems, including striking results showing that every smooth Jordan curve describes a rectangle, similar to any prescribed rectangle, and more generally, a cyclic quadrilateral, similar to any prescribed cyclic one. The talk will highlight the ideas behind these theorems and explain the connection to symplectic geometry. So I'm now happy to hand over to our speakers.
Well, thanks very much, Bogdan, for that very kind introduction. And thank you for the invitation to speak in this seminar on behalf of both myself and my collaborator, Josh Greene. Let's launch right into it. So there was a conjecture in 1911 made by Otto Toeplitz that's sometimes known as the Toeplitz conjecture, sometimes known as the square peg conjecture or the square peg problem. And this conjecture remains unsolved, and it says the following. Suppose you've got a Jordan curve, and our notation for a Jordan curve is always going to be gamma. Suppose you have a Jordan curve. What is a Jordan curve? Well, it's just a subset of the plane. Sometimes we'll think of the plane as R2, sometimes as the complex numbers C. It's a subset of the plane that is topologically homeomorphic to a circle. Equivalently, you can think of it as the image of an injective continuous map from the circle into the plane. All right, so suppose you've got a Jordan curve. The Toeplitz conjecture says that you should be able to find on your Jordan curve gamma 4 points that form the vertices of a square. So this conjecture is unsolved, it's old, and it's very easy to state. And these three ingredients make it quite appealing. And it's the starting point for today's talk. More generally, you think of this conjecture as suggesting a connection between the topology and the geometry of the Euclidean plane, where the role of topology is played by the Jordan curve and geometry by the square. All right, that's the conjecture. Let's think about one of the component pieces of that conjecture, the Jordan curve, to begin with. So here's a slide that contains, amongst other things, the images of some Jordan curves. In the top left-hand corner, that's a Jordan curve. It's the boundary of the country Jordan. The bottom left, that's a sort of fractal Jordan curve, just to show that things can be not so smooth when you think of Jordan curves, and they can be quite complicated. Top right is the region bounded by a Jordan curve. That's Camille the camel. It's a camel named after Camille Jordan. And then in the bottom right, well, that's an image of a smooth curve, a smooth map from the circle into the plane. But it's not a Jordan curve because it's got this point of self-intersection. That's a bit of a red herring. That's not the image of an embedded smooth curve. It's the image of an immersed smooth curve because it has this point of self-intersection. And we're going to start by thinking about immersed curves. So although this curve in the bottom right is immersed, could it be that we could deform it through immersed curves so that it becomes a properly an embedded smooth Jordan curve without a point of self-intersection? So I'm going to ask this question. It's going to seem like a little bit of a digression, but it's going to come back and tie up nicely at the end. So the question is, can we deform an immersed curve, that's a smooth curve with possible points of self-intersection, to an embedded curve, that's a smooth curve without points of self-intersection? So suppose we have an immersed curve. When can we deform it through immersed curves to become an embedded curve? Well, first let's parameterize it by a smooth map F. So this is a smooth map from the circle to the plane, whose image is the Jordan curve C, or sorry, is this immersed curve C. So here are two such examples on the left and the right of immersed curves. And because this map F is smooth, that means that at each point of the immersed curve C, there's a sort of well-defined tangent line. And we're going to think about how that tangent line moves around as we follow the map F around our immersed curve. So what do we get? So given a point on S1, that takes me to a point on the immersed curve C via the map F. There's a tangent line there, and the space of lines in R2, or the space of classes of parallel lines, if you like, is nothing more than RP1, which is topologically a circle. So you get a map from S1 to RP1. If you make some choices, such as, for example, you need a base point to define the fundamental group, then that map from S1 to RP1 gives you a map from the fundamental group of S1 to the fundamental group of RP1. RP1 is just topologically a circle. So this is a map from Z to Z. And well, what is that map? So if you look at the immersed curve on the left of the picture, and you follow the tangent lines as you travel around that immersed curve, you'll see that you wrap 0 times around RP1. You never make a full revolution around RP1. But if you look at the immersed curve on the right-hand side, you'll see that you wrap 2 times around RP1. So this map phi is either going to be multiplication by plus or minus 2, depending on your choices of convention, how you've identified pi1 with Z. So what doesn't depend on those choices is the image of this map phi. So you get a map from Z to Z. It's only really defined up to sine as I've written it. But the image of that map is just a subgroup of Z, and that determines a non-negative integer n, because any subgroup of Z looks like nz, where n is some non-negative integer. Now this map phi is insensitive to small perturbations of the immersed curve C, because it's just a winding number. So if you could deform your immersed curve to an embedded curve, then this number n that you have must agree with the n that you have for an embedded curve. And for an embedded curve, this n is always equal to 2. You can think of that, you can figure that out by thinking about the embedded curve, just the unit circle. As you travel around the unit circle, the tangent lines wrap twice around RP1. This is to do with the map from S1 to RP1 is a double cover. So there we are. So that's the condition. If we have an immersed curve and we know that we can deform it to an embedded curve through immersed curves, then this winding number n better be equal to 2. All right, that's going to feel like a digression, but we'll come back and think about this at the end of the talk. Right, so that's the first ingredient, Jordan curves. We talked about that. Inscribed squares. So The Toeplitz conjecture says that you can find 4 points on your Jordan curve at the vertices of a square. On the left, we've got our fractal Jordan curve. On the right, well, that's the region bounded by the Michael Jordan curve. And this slide is just making the point that all we're requiring is exactly that the 4 vertices of the square lie on the Jordan curve. We don't require, for example, that the edges of the square lie inside the region bounded by the Jordan curve. So this is what the Toeplitz conjecture is asking. So, apart from being a nice, old, unsolved, easy to state conjecture, why should one ask this conjecture? So let's think about that. So if you've got a favorite triangle, maybe the equilateral triangle or 3, 4, 5 triangle, you could ask, does every Jordan curve inscribe your favorite triangle? And it doesn't matter what your triangle is, the answer is always going to be yes. So asking kind of the inscribed triangle question rather than the inscribed square question always has a positive answer. On the other hand, well, suppose you got a couple of dissimilar ellipses. So that's ellipses of different eccentricities, the ratio of the major axis to the minor axis. And however you position these ellipses in the plane, they're never going to be, you're never going to get them to overlap in more than 4 points. If you think about it, what that means is that dissimilar ellipses can never inscribe similar pentagons. So, for example, a completely regular pentagon inscribes in the circle, but it can never inscribe in a non-circular ellipse. So the sort of pentagonal inscribed square question, whatever your favorite pentagon is always going to have a negative answer. You're always going to, in fact, find some ellipse that doesn't inscribe your favorite pentagon. And so quadrilaterals are sort of the midpoint. It's not obviously a false question. It's not an obviously correct question. It's kind of an interesting question. Why ask it about squares? Well, squares are just the first quadrilaterals that you think of. They're the most symmetric quadrilateral. So that's why one asks the square peg question. Why one poses the square peg conjecture. Here's some early history of the square peg problem. 2 years after it was posed, Emck solved it for smooth convex curves, and he considered the moduli space of inscribed rhombi, inscribed rhombuses, which is a one-dimensional space, it turns out, and has to pass through an inscribed square. So that's how he solved it for smooth convex curves. Schnirelmann, a bit later, solved it for smooth Jordan curves, and that's a Bohr's of mine. So Schnirelmann showed that every smooth Jordan curve always inscribes a square. This is roughly how his argument runs. So he has his favorite smooth Jordan curve, of course. Everybody has a favorite smooth Jordan curve. And he wants to show that it inscribes a square. So he starts with a non-circular ellipse that inscribes a unique square. And then he imagines deforming that ellipse until it becomes the smooth Jordan curve that he's interested in. And as you do that, well, the number of inscribed squares changes. But it always changes by 2 squares coming into existence or 2 squares blinking out of existence. So since you started with exactly 1 inscribed square, this is saying that the generic smooth Jordan curve inscribes an odd number of inscribed squares. And the thing about odd numbers is that they're never 0. And so that tells you that every smooth Jordan curve has an inscribed square. So that's roughly speaking Schnirelmann's argument. And you might think, well, once you've solved this for smooth Jordan curves, why haven't you solved it for all Jordan curves? Because if you have a non-smooth Jordan curve, for example, that fractal curve we drew earlier, you can arbitrarily closely approximate it by a sequence of smooth Jordan curves. Each one of those inscribes a square by Schnirelmann's argument. why can't I use some compactness argument to tell me that there must be a subsequence of these inscribed squares that limits to an inscribed square on the continuous Jordan curve? Well, the thing that's very difficult to rule out is that this sequence of inscribed squares on the smooth Jordan curves, it's hard to rule out that they might be getting smaller and smaller. And so they don't in fact limit to an inscribed square on the continuous Jordan curve, but they rather limit to a degenerate square where all four vertices coincide. And if Josh and I were giving a different talk today, we would talk about approaches to kind of try to overcome this problem. All right, brilliant. So I'm going to move on and tell you about a result from 1977 due to Vaughan. And if you take anything away from this talk, I both hope and expect that it's going to be this argument. So Vaughan came up with this in about 1977, but he didn't write it up. He told a bunch of people about it, and Meyerson wrote it up in the book Balancing Acts in 1981. And Vaughan was thinking about inscribed rectangles in Jordan curves. And his result is that all Jordan curves admit an inscribed rectangle. So Schnirelmann was putting a condition on the Jordan curve. He was requiring them to be smooth and then concluding that they have an inscribed square. Vaughan is not putting any condition on the Jordan curves, so they can be as non-smooth as you like. But he's allowing himself to consider inscribed rectangles instead of just inscribed squares. He shows that any Jordan curve admits an inscribed rectangle. And his argument is beautiful. I'm going to tell you what it is. So his first insight is to think about the diagonals of a rectangle rather than the edges. So let's do that. What is a rectangle? Suppose I give you 4 points, distinct points in R2, A, B, C, and D. When do we know that these 4 points are the cyclically ordered vertices of a rectangle? Well, here's a rectangle. And I'd like you, in your mind, to cyclically label the vertices of this rectangle A, B, C, D. Or if you have a whiteboard marker, you can do that directly on the screen of your computer. Just label these 4 black vertices cyclically A, B, C, D. And you'll notice that the line segment AC is one of the diagonals and the line segment BD is the other diagonal. And AC and BD, well, they have the same length as each other, and they also have the same midpoint as each other. That's that red dot. And in fact, if you give me any 2 arcs inside R2, so if you give me 2 arcs, AC and BD, distinct arcs, if those 2 arcs share the same midpoint and have the same length as each other, then they must be diagonals of a rectangle. This is Vaughan's first idea. So we're going to begin by thinking about the space of inscribed arcs in a Jordan curve. And then we're going to write down what it means for 2 of these arcs to be the diagonals of a rectangle. And it's just going to be that they have the same length as each other and the same midpoint as each other. But we're going to write that down a bit more mathematically and see what happens. So first of all, what is the space of inscribed arcs of a Jordan curve gamma? Well, when I say inscribed arc, I just mean an arc, that's a line segment with endpoints on the Jordan curve. So such a thing is really just determined by the 2 endpoints. So we're just looking at pairs of points x and y, where x and y lie in the Jordan curve. And we don't care about orientation of these arcs. So x and y are allowed to be unordered. And a fancy name for that space is the second symmetric product of gamma. We also allow x to equal y, so allow double points, and we think of those as being arcs of 0 length. So that's the space of inscribed arcs. It's just pairs of unordered points on the Jordan curve gamma. Fantastic. That's manifestly, topologically, a two-dimensional thing. It's almost got these two coordinates, x and y. So we should be able to identify it as one of our favorite two-dimensional spaces. So it turns out to be a Mobius band. Now its topology doesn't really depend on how gamma lies inside the plane R2. It just depends on gamma. Gamma topologically is a circle. So let's think about Sim2 gamma when gamma is the unit circle and see its Mobius band. So that's what we're going to do now. All right, so in the bottom right, there's our gamma, and I've labeled on gamma 5 inscribed arcs. They're the inscribed arcs which have an orange endpoint and a blue endpoint, and orange is not equal to blue. And there's the 2 degenerate inscribed arcs where you have a repeated endpoint, and I've labeled those in pink. And what we're going to do is take our two-dimensional space, Sim2 gamma, and we're going to define a map down to RP1. And how that's going to work is I take a point in Sim2 S1. S1 is our gamma here. And I send it to its parallelism class. So this is just it's a line in R2. And so that determines a point in RP1. And if it's a repeated point, if z equals w, I send it to the tangent line to the circle at that point. So all 5 of these points in Sim2S1 gets taken to the same point in RP1 because all 5 of these lines are parallel. And in fact, there's an interval's worth of points in Sim2S1 that get taken to the same point in RP1. And I've just drawn 5 of them there. But you can see the interval, and that interval has endpoints given by these 2 degenerate inscribed arcs where you've got this repeated double purple point. Fantastic. So what we've seen is we've got a map from Sim2S1 down to RP1, which is a circle, and living above every point in RP1 is an interval. So that tells you that Sim2S1 is an interval bundle over RP1. And interval bundles over the circle, well, there's only 2 of them. It's either going to be the cylinder or the Mobius band. Which one is it? Well, the boundary of Sim2S1, this just consists of all these purple points, which are degenerate arcs where z equals w. So these are the points ZZ, where z lies in S1. And that's, of course, connected. And the boundary of the cylinder is disconnected, whereas the boundary of the Mobius band is connected. So that tells you that Sim2S1 must be the Mobius band. More generally, Sim2 gamma is the Mobius band, any Jordan curve gamma. All right. Brilliant. So we've got our gamma lives inside R2. And we've got this space, Sim2 gamma, which is the space of inscribed arcs. And it's topologically a Mobius band. Now, Vaughan tells us how to map that Mobius band into upper half 3 space. So that's what's going on in this fairly busy slide. This is Vaughan's map of the Mobius band into upper half 3 space. So V stands for Vaughan here. And V is a map from this Mobius band, Sim2 gamma, into R2 times the non-negative real numbers. So that's upper half 3 space. And what this map is, well, I think of it as the midpoint distance map. First 2 coordinates, that's a point in R2. And the first 2 coordinates, well, ZW gets sent to Z plus W over 2. That's the midpoint, so it's labeled in red. Whereas the third non-negative coordinate, that's the length of the arc, ZW. And that's labeled in blue. So Vaughan takes this Mobius band, which consists of all the inscribed arcs of gamma, and he maps it into upper half 3 space, and the coordinates tell you exactly the midpoint and the length of each of these inscribed arcs. Fantastic. What happens to the boundary of the Mobius band? So the boundary of the Mobius band is just those points where z equals w. So think about what v does to z comma z. Well, it maps it to z plus z over 2 comma 0. So it maps to z comma 0. So as z travels around our Jordan curve gamma, zz gets taken to z comma 0. So the boundary of the Mobius band just gets taken to a copy of the Jordan curve gamma that lies on the boundary of upper half 3 space. That's, well, it's hard to draw a picture of that, but that's meant to be indicated in the bottom right-hand corner of this slide. You've got this Mobius band that's going to live in upper half 3 space above the Michael Jordan curve, and the boundary of the Mobius band is going to trace the boundary of Michael Jordan. All right, brilliant. Now, what about this Mobius band? Could it possibly be embedded in upper half 3 space? Well, let's hope not, because self-intersections of this Mobius band correspond to inscribed rectangles. If you have 2 points, 2 arcs, ZW and XY, that get taken to the same point in upper half 3 space, that tells you exactly that the arc ZW and the arc XY must have the same midpoint, because they have the same first 2 coordinates under V, and they must have the same length, because they have the same non-negative third coordinate under V. So in other words, if this Mobius band self-intersects, if an arc ZW gets taken to the same place as the arc XY, then ZW and XY are diagonals of an inscribed rectangle. So inscribed rectangles in gamma correspond to self-intersections of this map V, because Z, W, X, and Y, they're all points on gamma. So does this Mobius band self-intersect? Well, okay. So the answer is yes. And you're going to have to look at the little picture of me while I wave my hands about to tell you why that is. So you've got your Mobius band, it lives in up half 3 space, and its boundary is taken to the Jordan curve in the boundary of up half 3 space. Take that Mobius band and reflect it so you get a copy in lower half 3 space. So then the copy in up half 3 space is joined to the copy in the lower half 3 space along the Jordan curve. What you've got is a Klein bottle in just 3 space now. That's the union of 2 Mobius bands. And there's no way of embedding a Klein bottle in R3. That's just a closed, non-orientable 2 manifold. You can't embed it in R3. So this Klein bottle must have points of self-intersection. And because the upper Mobius band doesn't meet the lower Mobius band, it must be that there must have already been self-intersections of the upper Mobius band with itself, and then corresponding self-intersections in the reflection. So that's the argument. Here's that written down. You reflect this Mobius band across the boundary of half 3 space. That gives you a Klein bottle just in 3 space, and there are no embeddings of the Klein bottle into R3. So there must have been self-intersections already present in this Mobius band. So that leads us to the question, can we do any better than just one rectangle? And at this point in the talk, I'm going to hand over to my co-author, Josh Greene. So he's going to have to share his screen.
Thanks. Bear with. Let's try this. Could you let me know if this looks correct?
Yeah, I see the slide.
Okay. I'll take it from here. Thanks, Andrew. So to follow on Andrew's presentation, the argument that he just described shows that there's always at least one rectangle inscribed in every Jordan curve in the plane. And if you think about maps from the Klein bottle into R3, you actually get a whole lot of self-intersection. You're accustomed to the standard Acme Klein bottle model, which exists. You see a whole loop of self-intersection. I'm sorry, I don't have one to display. But that whole loop of self-intersection suggests that you should be able to find whole loops of rectangles inscribed in Jordan curves or something like that. In the wake of that observation, there arose this problem, which is stated here. And it's stated here for a smooth Jordan curve because we've sort of given up on trying to solve the square peg problem for a continuous Jordan curve. So the problem asks if it's the case whether every smooth Jordan curve inscribes every rectangle, every similarity class of rectangle. And to illustrate that, I have here shown a picture of an ellipse. And what you see are 4 inscribed rectangles in it, which suggest a whole sweep out of rectangles moving from the degenerate case of the major axis, horizontal, to the minor axis, vertical. So for any prescribed rectangle, a rectangle is codified by its aspect ratio, the proportion of the side lengths. You see for each aspect ratio of rectangle, a copy of it inside of this ellipse. In fact, you see 2, apart from the case of the square, which has aspect ratio 1. So that's the problem. Is it the case that for every aspect ratio of rectangle, it's possible to find an inscription of it into any given smooth Jordan curve? Okay, so this got known as the rectangular peg problem, and it appeared in this popular book by Ian Stewart under this name, amongst other places. And this was a problem which we undertook to solve. So I'll tell you about that. But if you were feeling ambitious, you might ask whether seeking rectangular inscriptions is really the thing you ought to be doing, or whether you might be able to go further. So if you dwell on the case of the unit circle for the moment, of course, it inscribes more quadrilaterals than simply rectangles. It inscribes all the cyclic quadrilaterals as well, which by definition are those sets of 4 points on the unit circle. So if you were feeling optimistic, you might ask, well, is it the case that any set of 4 points which inscribes in the circle, is it the case that every cyclic quadrilateral actually inscribes in every smooth Jordan curve? And so when we're talking about inscribe now, just to emphasize, I'm thinking I have a given 4-point set, and I want to apply some orientation preserving similarity to the plane, which carries that 4-point set to a target Jordan curve. Okay. Hopefully that's clear. If you're wondering which 4-point sets inscribe in all smooth Jordan curves, then you're constrained to those which in particular inscribe in the unit circle. So this would be the most general smooth peg problem you could ask, as the frame title suggests. Okay, so this is a generalization of the rectangular peg problem, and it's being asked here for a smooth Jordan curve. That's for a good reason. If you're thinking in this generality for quadrilaterals, it turns out this doesn't have an affirmative solution if you relax the smoothness condition on the Jordan curve. In fact, if you pick a cyclic quadrilateral, which is not a trapezoid, it's always possible to produce a continuous Jordan curve, in fact, a triangle, which fails to inscribe it. And that's kind of an elementary construction, but it takes a little effort to see why that is. So there are continuous Jordan curves which fail to inscribe cyclic quadrilaterals if the cyclic quadrilateral is chosen to be anything other than a trapezoid. So if you're hoping for an affirmative solution to this cyclic quadrilateral peg problem, smoothness of the Jordan curve had better play an essential role in the solution. And that's where we're heading toward in this talk. So I'll give a proof of this, solution to this problem, and we'll see directly how smoothness gets used. So I shall continue. This comment got addressed. And basically so did this one. So this is the solution of the cyclic quadrilateral peg problem. Every smooth Jordan curve, for every cyclic quadrilateral, you can find the inscription. Okay. So let's see why this is. To get started, let's dwell on what makes a quadrilateral cyclic, if that property can be characterized, and there is indeed a characterization due to Euclid, which we'll find very useful. If we have 4 points in convex position, then we can draw the diagonals of that convex quadrilateral, and they'll intersect at a point in the interior of the quadrilateral. And that point will dissect the 2 diagonals into 4 lengths. And you can measure those lengths and take the product of the lengths into which one diagonal is divided and multiply the lengths into which the other diagonal is divided. And it works out that if those products agree, then the quadrilateral is cyclic, and if they disagree, then not. And this is a result you can prove based on similarity of triangles, and I'll refer you back to your high school self, who undoubtedly knew a proof of this result for math competitions. Okay, so this is a characterization of the cyclic condition, which we're going to use. And just like a similarity class of rectangle is determined by a single value, the aspect ratio, or equivalently the aspect angle, the angle at which the diagonals of the rectangle meet. Similarly, a similarity class of cyclic quadrilateral is determined by 3 parameters. So they form a 3-parameter family, and they're given by, those 3 parameters are the ratios of these lengths into which the diagonals divide one another, A over B and C over D as in the picture, and that angle phi, which you could take to be the angle measured from the red into the green, going from A to C in this picture. Okay, so that's elementary stuff. And now we do something that's going to look a little unusual, so it'll take a moment to unpack. So earlier, Andrew was describing to us a way of taking a pair of points on a continuous Jordan curve and associating with that pair, that arc, a target in upper half space, R2 times non-negative reals. And here, something a little bit different is happening, but it's similar to what we did before. What we see instead is arcs on gamma now are being taken into product of the complex numbers with itself. Okay, and so what's happening is that first coordinate should look reminiscent of taking the midpoint, but here it's a weighted combination. It's a convex combination of the points chosen, weighted by this parameter r. And you're supposed to think in terms of the previous slide that r is, the proportion of that line segment taken up by the subsegment from Z to that marked point, okay? So in any case, that first coordinate is supposed to be picking off that red point on that arc ZW. And the second coordinate is, previously we were interested in the length of the segment ZW. Now we are recording the difference between Z and W. So we're recording that vector. And this is a complex number. And it's being weighted by this funny looking square root thing. Okay. But it's just some real multiple of that vector ZW. Okay. So this is the map we study. So this is a mapping from a 2 torus into a 2-dimensional complex vector space. Okay. So it looks a little funny, but it's what we are going to use. And we passed over this remark. And we also passed over this remark. Okay. So away we go with this mapping. One final remark is that previously, if you looked at the degenerate arcs, you'll recall that in Vaughan's argument, those got thrown onto a copy of the Jordan curve sitting on the boundary of upper half space. And now instead, it's being taken onto a copy of the curve, gamma times 0, sitting within C times 0, inside of C times C. So there's this special loop. This loop plays a special role going forward. Okay, and now along comes a transformation, R phi. R phi is a mapping of 2-dimensional complex vector space to itself. And what it's doing is it's simply rotating the second coordinate through an angle phi. And what we are going to be interested in is the intersection between the torus from the previous slide, which depended on a parameter r, and another copy, a torus which depends on another parameter s, rotated by this mapping R phi. Okay. So this picture is trying to convey the answer to this question. And I think rather than thinking hard through how all this works out, the punchline is going to be that the pairs of arcs which correspond to the intersection points between these tori correspond exactly to the cyclic quadrilaterals inscribed in this Jordan curve gamma, which correspond to the 3 parameters r over 1 minus r, s over 1 minus s, and phi. And somehow buried in here, we are using Euclid's characterization of the cyclic quadrilateral property. So the punchline, much like the punchline we saw in the earlier argument due to Vaughan, is this one, that the intersection points between this pair of tori sitting inside of C2 correspond exactly to inscriptions of a particular class of cyclic quadrilateral, depending on those parameters r, phi, and s into gamma, along with this somewhat pesky loop, gamma times 0. So that's sitting there on both sides. So the degenerate inscriptions of the cyclic quadrilateral on the left correspond to this loop gamma times 0 on the right. So what we would like to show is that what we see on the right, that intersection, is more than just this pesky loop, that there are some other interesting intersection points sitting there, because those are going to give us the desired inscription of the cyclic quadrilateral. Now, the special property that allows us to move forward, and this is crucially using the fact that the curve gamma is smooth, is that these tori which we have constructed in C2 work out to be Lagrangian tori with respect to a symplectic structure on C2. One is written here. This is the standard symplectic structure on C2. Okay, so this is a closed non-degenerate 2 form. And what we are looking at are these subspaces, these tori. And these tori have, if you look at a tangent plane to one of these tori, you can restrict the symplectic form to pairs of vectors in it. And it works out that when you restrict that 2 form to any pair of vectors tangent to one of these tori, you get an evaluation of 0. And that's the Lagrangian condition. Okay. And the fact that these have half the dimension of the ambient space. And this reformulation of the problem is meaningful because now that we're thinking of inscriptions of a cyclic quadrilateral as intersections between a pair of Lagrangians, we have available a whole host of techniques. So there's, we have 40 years of symplectic geometry to lean on to answer questions about Lagrangian intersections, and we can apply them to our particular Lagrangians here. Okay. So these questions are often amenable to geometric techniques, and specifically symplectic geometric techniques. And we're going to get the desired result by leaning back on an old result due to Polterovich and Viterbo. They're old, 35 years old. Okay, and I know we've got just a couple minutes left, so I'll move a little quickly. So as discussed, these tori have a loop of intersection, and we'd like to show they intersect somewhere away from that. And this intersection is a little better than pesky. It's a clean intersection, and a clean intersection is modeled on just a pair of coordinate axes intersecting in a transverse point, being multiplied round by a circle. So you imagine you have a bit of a sheet of one torus, another sheet of another torus coming through, and they meet in this way, just like the product of an X with a circle. And you can take a cross section of that X and smooth it like a pair of arcs from a hyperbola and multiply that round by a circle. And so there's this cut and paste that we can do along that loop of intersection between this pair of tori. So I'm going to take these tori and do somewhat of a violent operation. I'm going to remove that loop of intersection between them. I'm going to smooth it out and get, in that way, just a single Lagrangian. Now that Lagrangian is going to intersect itself. It's going to be a torus, but where itself intersects is giving us the inscribed quadrilaterals that we are looking for. So after we've done this smoothing, we've got a single immersed Lagrangian torus, and we want to show that it self-intersects. Once we show that it self-intersects, we're done. So how to do that? Well, this echoes back to the slide on the second or third slide from the talk, on which Andrew's spent quite a bit of time. This is an argument to show that this torus that we've built is not embedded by looking at a quantity very similar to a winding number that Andrew was discussing earlier. And just so it flashes before your eyes, there's this generalization of a winding number called the Maslov index. And the Maslov index associates to loops on a Lagrangian integers, which measures something about how the Lagrangian tangent planes around it. It's measuring homotopy classes of Lagrangian planes around it. And so this is a basic invariant of a Lagrangian immersion in a symplectic vector space. It was really, it's due to Maslov, but it was really promoted and popularized and brought into focus by Arnold. And what Polterovich and Viterbo showed is that if you have an embedded Lagrangian torus in standard symplectic C2, you can always find a loop on it with winding number Maslov index 2. But it works out in our construction, our immersed Lagrangian has a Maslov index, well, Maslov class, which is a multiple of 4, doesn't contain a loop of Maslov index 2. And the only possible conclusion then is that whatever immersed Lagrangian we were looking at is not embedded, it self-intersects. And that therefore gives the inscription of the corresponding cyclic quadrilateral into the corresponding smooth Jordan curve. Okay. So that's the end of that argument. So that solves the cyclic quadrilateral peg problem for smooth Jordan curves. And I'll just note in the last 10 seconds, Andrew spent some time talking about Klein bottles inside of R3. Prior to getting the case of cyclic quadrilaterals, we had just addressed the case of rectangles. So that was a step along the way. And the way that we addressed the case of rectangles was a little bit different. What we got in that situation was an immersed Lagrangian Klein bottle in R4. And it turns out that there is no embedded Lagrangian Klein bottle in standard symplectic R4. And that fact plays the same role as the Polterovich-Viterbo result that we just used. So the fact that there's no embedded Lagrangian Klein bottle in R4 delivered the case of rectangles. And then working a little harder, we realized we could get the case of cyclic quadrilaterals using the Polterovich-Viterbo theorem. Finally, there's this wonderful, now I think a dozen-year-old survey by Benjamin Machka in the AMS notices, and it contains a very nice history of this problem. It's a little, it's a wonderful read. It may be a little bit dated now, but it still contains a lot of great stuff in it. And I'll leave it there, knowing that now we're a little bit over time. So thank you very much on behalf of me and Andrew.
Yeah, thank you. Thank you very much for your presentations. So I will now allow everyone to unmute themselves and ask questions. And from the very beginning, you can also show your faces if you like. Okay, so I will start with my question. So I recently see in arXiv some great, nice progress which you and other people made in the non-smooth case, because that's about smooth case. You talk about in the non-smooth case. Can you, tell all people about this? So what was proved recently in non-smooth case?
I could say something.
Yeah.
And then maybe Andrew. Going further, it was clear to us from the get-go that it would be useful to apply the techniques of Floer theory to this problem. And so the kind of idea is we have, let's say we have a rectangle. Let's say we have a smooth Jordan curve. And let's say we want to show that the set of inscriptions from this rectangle into this Jordan curve is a non-empty set. Okay, I just gave you an argument, but there's a kind of a Floer theoretic philosophy to how you might proceed. You could take this set the set of inscriptions of a given rectangle into a given smooth curve. And you could attempt to define a homology. So you take this set you want to show as non-empty and you form the vector space freely generated by its elements. And then you try to define a differential on this vector space, so some endomorphism that squares to 0. And supposing you have done that, then you can look at the kernel of this endomorphism, divide it by its image. That's what you would call the homology of this chain complex. And you would get a group. And if you could argue that this group is non-zero, then it means that the set you started with had to be non-empty. Okay. And as it turns out, we succeeded in defining such a theory using the techniques of Lagrangian Floer homology, thinking about inscriptions of a rectangle in a smooth curve as a set of intersection points between a pair of Lagrangians. So we designed a Floer theory then, which recovers the fact that every rectangle inscribes in every smooth Jordan curve. Okay. And now I'll pass the rest of the answer to Andrew.
Thanks. And so to get, this Floer theory comes with more data than just being a non-empty vector space. It comes with a filtration. So associated to elements as vector space is a real number. And that real number has something to do with the size of the inscribed rectangles that represent the homology classes. And so it's really that filtration, which in the business is known as a spectral invariant, that we're able to leverage to sort of surmount this problem of shrink out when you approximate a continuous Jordan curve by a sequence of smooth Jordan curves. What stops your inscribed squares, inscribed rectangles from shrinking out? And so using this filtration, we're able to obstruct shrink out in some number of cases. And other people are able to use similar ideas to obtain other results in this way. Yeah, so that's it. It's spectral invariants are part of the package of Floer homology, and they were what we use to obstruct shrink out.
Sorry, less technical answer, just no technicality, just tell us what you proved recently exactly. So in non-smooth case, what it was? Some proportion of rectangles or what?
Yeah, if you have any continuous curve, there's a quantity you can associate to it. We've been calling the Bieber-Bach number, for lack of a better term. It's a number between 0 and pi. Okay, and basically measures how round the curve is. It's pi exactly when the curve is a circle. Okay, so you've got this number, and so it's great. What we show is that there's a set of angles whose measure is bounded below by the Bieber-Bach number. And if you pick any angle in that set, that Bieber-Bach size set, you pick any angle in that set, then you can find an inscribed rectangle in your Jordan curve whose diagonals meet at that angle. So you're getting a big proportion of all rectangles inscribing in any given continuous Jordan curve. Annoyingly, though, you know that result doesn't tell you any particular one that inscribes. In particular, I mean, you could have Bieber-Bach number, as close to pi as you like, and not know that you're getting an inscribed square from this result. So it's a bit of a shortcoming of that result, but it's the best result that we know now for continuous Jordan curves.
Okay, thank you. And the ultimate goal, the most general conjecture, is that every rectangle in every curve, yeah?
I think you could ask that, but you could even ask, it's conceivable that isosceles trapezoids could inscribe in all continuous Jordan curves, or it could be that an audience member finds a counterexample. That could always happen.
Okay, so Siddharth, you have a question, you raise your hand. Yeah, can you ask the questions now?
Yes. So just wondering, do you think it's possible to apply similar techniques to questions that ask about what types of regular qualitobes can be inscribed on rough, smooth hypersurfaces that are embedded in Rn for finite n?
No. So the problem is, well, at least not directly. So what's special about Jordan curves inside R2 is that they're already Lagrangians. So these are half-dimensional submanifolds of R2 on which the symplectic form vanishes. So that's anything. So all smooth Jordan curves are Lagrangians, and then really what's being used is that a product of a pair of Jordan curves is also Lagrangian. If you try and play the same game with hypersurfaces inside Rn, say just say smoothly embedded spheres in R3, well, you kind of lose this this Lagrangian property, and so directly it's difficult to see how that would work. We can sort of generalize in a different direction, which is, you can think of inscriptions of a cyclic quadrilateral as looking for a linear map from C to C. So something looks like Z goes to AZ plus B, that take the 4 vertices of your favorite cyclic quadrilateral onto your given smooth Jordan curve. Because Z goes to AZ plus B, that's just a similarity of the complex plane. So you can raise the number of vertices. In particular, you could ask for hexagons, whether you can throw them onto any smooth Jordan curve via a quadrilateral, via a quadratic in Z. And it turns out that that is something you can do. And to argue that, we needed to think about Lagrangians inside C3 rather than Lagrangians inside C2. So it does admit some generalizations to sort of higher order questions, but I think not directly in the way that you suggest of hypersurfaces inside Rn.
And just thanks for the question. Yeah, it's a really natural one. Yeah, I mean, the symplectic techniques kind of push us in one direction, whereas there are these really interesting geometric conjectures that they just don't seem to get to. So that it's tantalizing. You should look at, if you haven't, this survey of Benjamin Machka in the AMS notices from 2014. He takes up that problem. And I'd recommend having a look at what the open problems are there and then tracking down what's happened since then.
Okay, there is also one more question in chat. Can you please answer it?
I've been dwelling over this question by Ismail. Oh gosh, I just don't perhaps know enough about what's happening in data science to come up with any other examples. But maybe it puts in your mind now symplectic geometry or some rudimentary algebraic topology as a kind of a powerful tool, which you could just kind of keep in your arsenal and try to hit on any particular problem. But I cannot think of any examples in that domain just as a result of my ignorance of it.
Okay, thank you, everyone. Thank you for attending the talk. Thank you for your presentations. Yes, and we
Thanks
finish
very
now.
much. All right.
Okay.
Wonderful forum.
Thank you.
Thank you.
Bye.
Bye-bye.